Hey guys, Mr. O'Sullivan here. Hey, let's go over practice exam number 4. And so as we dive in, uh, part A, the longer question, we're given a table. So it says the twice differential functions f and g are defined for all real numbers x. Values of f prime, g, and g prime are located, or for selected values of x are given in the table above. Okay, so we got f of x, f prime of x, g of x, and g prime of x are given for these x values and also for those intervals on x. Okay, so we're asked to do 1, 2, 3, 4, 5, 6 things with that information. Okay, so part A says find the x-coordinate of each relative minimum and each relative maximum of f on the interval -1 to 8. Okay, so I'm kind of checking my interval here, -1 to 8. And it looks like that's going to include the entire table. And if I'm looking for a relative min and a relative max of f, I'm remembering that a relative min on f is going to be where f prime changes from negative to positive. I'll just double check. I'll kind of just make a relative min, just draw a relative min. That's my relative min on f. And then I'm just drawing tangent lines. Hey, that tangent line's got a negative slope. I draw another tangent line after the relative minimum, and that one has a positive slope. So my derivative f prime went from negative to positive, okay? And a relative max on f is going to be indicated by the derivative f prime going from positive to negative. There's my max. There's a positively sloped tangent line, and then after the max, my tangent line would have a negative slope. Okay, so really I got to key in on is my rho for f prime. Okay, so I'm looking at f prime right there, and I see that it's positive on that interval from -1 to 0, and then it goes negative. Okay, and then it stays negative kind of for the rest of the interval. So the only action I've got going on is when it changes from positive to negative. Where does that occur? At an x value of 0. Okay, so let's see, positive to negative. That means I've got so I'm just going to say f has a relative max when x equals 0, indicated by f prime going from positive to negative. Okay, that's all I've got. There's no relative minimums or anything like that, and no other relative maximums other than that. Okay. Part B says let h be a strictly decreasing and twice differentiable function such that h prime at 2 equals f prime at 2, h prime of 8 equals f prime of 8. And we're given this definite integral to evaluate. Okay, well, the key here is to look at the integrand of our definite integral and see that, we have got nearly the derivative of our kind of lower function here in the denominator. We have the derivative of that almost in the numerator. Okay, so hopefully you kind of recognize that. This is kind of one of those where we see if you might have seen it where it was dx of natural log of u, and the derivative of that, I'm showing it kind of the aspect of the derivative. The derivative is going to be u prime over u. And so really, we're kind of seeing that pattern in the integrand. Okay, so and again, almost seeing that because we don't have the entire derivative of h prime of 2x. We're lacking the 2, right? Okay. So I'm just going to write this one. Start here. 1 to 4, h double prime 2x over h prime 2x dx. Okay, if we recognize that, and again, this is pretty heavy on the symbolic nature. That's kind of what they're checking on. Really, with this, the antiderivative is going to be 1/2. And why do we have that 1/2? We have that 1/2 to kind of compensate for, or to take care of, take care of that 2 in their h prime of 2x. You think of it this way. If I was taking the derivative of h prime of 2x, I'd have to multiply by the 2. And because I'm integrating, I'm going to divide by the 2 or multiply by 1/2. Okay. So this is going to be 1/2 of the natural log of 2x. Okay. Nope. That's a lie. It's going to be 1/2 of the natural log of the entire denominator. That is h prime of 2x. Okay. Now again, if I had time, what I could do is I could go ahead and take the derivative of what I just came up with as my antiderivative, and I should come back to my entire integrand. Okay. You can trust me on that one, or if you got some time and you want to go ahead and do that just to make sure that's what we got, feel free. Okay, and then I'm going to bring over my bounds, 1, 4, and then I'm just going to FTC part 1. I can, if I want, I can kind of pull that 1/2 out, and then this is going to be the natural log of h prime at 2 times 4, my upper bound, minus the natural log of h prime at 2 times my lower bound of 1. Okay, so 2 times 4 is going to give me 8. 2 times 1 is 2. And now here's where I can take that substitution that they gave me, that h prime at 2 is equal to f prime at 2, and h prime at 8 is equal to f prime of 8. So I can rewrite this as 1/2 the natural log. Instead of h prime at 8, I can write it as f prime of 8 minus the natural log of not h prime at 2, but f prime at 2. Okay. And then properties of logarithms, I can write this as 1/2. I'm subtracting my logarithms. I can condense that into a single logarithmic expression. So it's going to be 1/2 natural log of f prime at 8 divided by f prime at 2. Okay. Which is going to be equal to 1/2 the natural log. Okay. Now here's where I want to go up to my table and find f prime of 8 and f prime of 2. F prime of 8, f prime, again, I'm in that f prime of 8 is -6, and then f prime of 2, f prime of 2 is -1. Okay, that's a numeric answer. I'm going to just stop right there. Okay, that is my value of that definite interval. Okay, use a right Riemann sum with 4 subintervals to estimate the definite integral from -1 to 8 of f of x dx. Okay, it's a right Riemann sum, 4 subintervals, and it's for f of x. Okay, so I just want to make sure I'm on the right row. And, it'd probably be handy just to take this piece of the table that I need, f of x, just bring that down where I'm working on this one. Okay. and it's a right Riemann sum. So what I want to do for each interval is, and here's my four intervals. And okay, here's one, there's two, there's three, and there's four. That makes sense. I see how the interior ones kind of overlap. Okay, so I guess the first thing I want to do, a right Riemann. So for each interval, I want to kind of like just circle the y value on the right side of the interval. So for this first one, it's going to be the 5, the 3, the 0, -2. I'm not even going to mess with the 3. If it was a left Riemann sum, I'd use that one. I wouldn't use the -2. Okay. All right. So now I'm going to estimate this. I'm just going to do this. 1/8 f of x dx. Use my approximation symbol. It's going to be approximated by my right Riemann sum. Okay. So I need, first off, it looks to me like my delta x are not going to be consistent. So I can't kind of factor that out and just show it times that quantity of my y values. So I'm just going to look here. Okay, -1 to 0, it's going to be 1. So it's going to be 1 times 5 plus from 0 to 2, 1 is 2. So this is going to be 2 times y value of 3. And then 2 to 4, that's 2 again, plus 2 times my y value of 0. And then my last delta x from 4 to 8 is 4 times my y value of -2. 4 times -2. Okay. Good news is that's a numeric answer. That gets me my answer point, also gets me my right Riemann sum. Okay. Evaluate the limit as x approaches 2 of g at x cubed over e to the third minus e at f of x. Okay. Gosh, is anybody thinking L'Hopital? I mean, I just look at this, and if I see kind of a rational function that's like more complex than just like a quadratic or something like that over a quadratic or some linear function or something like that, I'm probably guessing it's L'Hopital. Again, now a big common mistake is for somebody to kind of like do L'Hopital and to start out by just saying, oh, okay, well, I'm just going to plug and pray and I'm going to write this. Okay, do not write that because that's bad math. If you write that, you're basically saying that you're done. The answer is the indeterminate form. Okay, well, indeterminate form, 0 over 0 or infinity over infinity or negative infinity over negative infinity or any of the indeterminate forms can never be the answer to a limit expression. Okay, a limit expression is either going to be the limit does not exist, DNE style, okay, or a number, okay, 0 or -2 or 5 or 6 or whatever, but it's never going to be the indeterminate form. The indeterminate form just shows that we've got more work to be done, either L'Hopital or we can cancel, factor and cancel, simplify something, okay, multiply by, rationalize a numerator, denominator, something like that. So we never ever want to write this. What we want to do is we do have to show, though, that L'Hopital can be used. And so the way we want to do that is to write two separate limit expressions, one for the numerator, one for the denominator. So I want to write it as the limit of g at x cubed as x approaches 2, okay? I can kind of evaluate this, and so that's going to be g at 2 cubed. So that's going to be g at 8. And I'm going to go to my table for that. And I bet you a dozen donuts, g at 8. Sure enough, there's my g. There's 8. It's 0. Surprise, surprise. Surprise, surprise, surprise. Okay, now I can write equals 0. Okay, now I'm going to do the same thing for the denominator. So limit e to the third minus e to the f x, this is as x approaches 2. So this is going to be e to the third minus e to the f at 2. And then I'm going to my table to see what f at 2 is equal to. And I would bet a dozen donuts that it's going to be 3. F at 2. There's my f. There's 2. Sure enough, it's 3. So I get, for the denominator, e to the third minus e to the third, which is equal to 0. So I see 0 in the numerator, 0 in the denominator, and now L'Hopital can be used. Okay, so now what I'm going to do is I'm going to go, when x approaches 2, d dx, g at x to the third, over d dx. I'm just showing that I'm taking the derivative of the numerator and the denominator, e to the third minus e to the f of x. Okay, so this is going to give me a new limit expression, still as x is approaching 2. My new numerator is going to be chain rule g prime at x to the third times 3x squared, okay, the derivative of the inside function, okay, over, well, d dx of e to the third, that's a constant, so that goes away. So now d dx of negative e to the fx is going to be negative e to the fx times the derivative of the inside function, which is f of x, is going to be times f prime of x. Okay, all right. I'll plug and pray. So I'm going to get g prime at 2 cubed, or 8, times 3 times 2 squared, all over negative e to the f of 2 times f prime at 2. Okay, not a numeric answer. I got to keep going. So I'm going to kind of come down on the next line there. And g prime of 8. So now I'm just kind of like fishing numbers from the table. G prime of 8. G prime of 8 is negative 3. Just going to write this down here. So negative 3 times 3 times 2 squared, all over negative e to the f of 2. I saw f of 2 somewhere. Oh, there it is. F of 2. F of 2 is equal to 3. So this is negative e to the third. Okay, and that's what the table will say. Times f prime at 2. F prime at 2. F prime at 2 is negative 1. Then I'm done. Okay, numeric answer. Don't hurt yourself. Okay. All right. All right. Part E. Is there guaranteed a value C? Okay. I hope you guys are at the point where when you see those magic words, is there guaranteed a value C, or must there be a value C, or how do you know that a C exists, you know, et cetera, that kind of language. You know, okay, we're talking about some kind of theorem. Okay. Now it's just a matter of which one. Okay, is it IVT? Is it mean value theorem for derivatives? Is it mean value theorem for integrals? You know, what are we talking about? Squeeze theorem, Rolle's theorem. Okay, is there guaranteed a value C in the open interval -1 to 8 such that f double prime at C equals 0? And explain. Okay, well, when I see f double prime at C equals 0, and then I go back up and I compare what I'm given in my table. I'm given f, I'm given f prime, I'm given g, and I'm given g prime. What I'm not given in my table is f double prime of x, okay, which is what we've got. Here's the question right here, part E, you know, f double prime. So I'm thinking, okay, if I would have had f double prime in my table, and they're saying, is there guaranteed a value C in the open interval -1 to 8 such that f double prime at C equals 0? and I've got both the same function referenced at the stem of the question and given in the table, I'm thinking IVT, okay? But because it's kind of one off and I don't have F double prime in the table, but I do have F prime, then I'm thinking MVT for derivatives, okay? So, again, I think, hopefully you're starting to get to the point where you're seeing that. Just a general rule of thumb, probably not a bad idea to maybe start with, the theorems that you might see if it's fitting the situation. Start with mean value theorem for derivatives, okay? I'm guessing prior history has kind of said that, that's a pretty commonly tested one, because that's really bringing to the forefront the idea of how the derivative relates to, the average rate of change. IROC and the instantaneous, back up, IROC equals the average rate of change, the slope of the tangent line equaling the slope of the secant line, okay? I mean, that's all, just different ways you can think of mean value theorem for derivatives, okay? Okay, so if that's the case, let's go down that road. And so we're basically saying mean value theorem for derivatives, and it would be good to kind of restate, this is what you should do once you've kind of identified what the theorem is to restate the conditions, but kind of as they've occurred, okay? Because we're saying that the mean value theorem for derivatives applies, so that must mean that the ifs are true, our conditions are true. So we're going to start out by saying because f prime of x is continuous on the closed interval from -1 to 8, and second condition also met, f prime of x is differentiable on the open interval from -1 to 8. Okay, those are the two conditions, mean value theorem for derivatives. Then there is at least one x equal to c in the open interval, just like they've got here. I'm just writing it in interval notation, -1 to 8, in that open interval, -1 to 8, such that what? Such that f double prime at c equals 0. And then what's the other side of that? This is kind of saying that the slope of the tangent line at x equal to c is equal to the slope of the secant line. And that's going to be, this is where we're kind of like one up from that second derivative. So it's going to be f prime at 8 minus f prime at -1 over 8 minus -1, okay? Now, I can't leave it there because I've got that function notation, so I just need to take that out. F prime at 8 and f prime at -1. So f prime at 8, back to my table, f prime, I'm in that, f prime at 8 is -6 minus f prime at -1. I am pretty sure that's going to be 3. F prime, same line. F prime at -1 is going to be, f prime at -1 is 1, okay? So that, oh, okay. I see what's going on here. I got a little carried away. I was only looking at the endpoints of my interval that I'm given here. Well, I can kind of shorten, I can be anywhere within that interval from -1 to 8. And I can almost kind of like just say, okay, well, I know this has got to work out to be 0. So my numerator here has got to be 0 right here. So what I'm going to do, I'm backing up. Okay, I'm backing up here. And I'm kind of just going to fudge and say, okay, again, looking at that F prime row. So I'm right, looking at F prime. I'm looking for, boom, right there, 0 and 0, those values there. So I'm going to use 4 and 0 as my X values. So I'm going to do F prime at 4 and F prime at 0. F prime at 4 minus F prime at 0. Okay, now the good news, 4 is in that interval from -1 to 8, and 0 is also in that interval. So that's okay. I can use a shorter interval than what I'm given, to start with, the sub-interval within that, over 4 minus 0. And I just know that F prime of 4 is 0, 0 minus 0 over 4 minus 0, and that equals 0. Okay. Okay. So, and I don't even have to say anything about MDT for derivatives. Okay. All right, guys, we're in the home stretch. Looking at the last part of the first question there. So it's asking, let h of x equal f of x over g of x. Write an equation for the line tangent to the graph of h at x equals -1. Oh my gosh. Here we go again. Done this a bazillion times. So we're going to probably start with our, not probably, we are definitely going to start with our point slope form of a linear equation. So we got y minus y1 is equal to n times the quantity x minus x1. Okay. We can kind of help ourselves out a little bit and say, really the m, that's going to be, if we're looking for the equation for the line tangent the graph of h, well, that's going to be the slope of the tangent line. So that's going to be h prime at x equals -1. So it's really going to be h prime at -1 times the quantity x minus -1. Then the other side of my equation is going to be y minus, well, y sub 1 is really going to be h at -1. Okay, well, I'm not done because I've got, these two expressions in function notation that I have to take care of. Okay, come up with values for those, then I'm done. All right, well, let's look at the y value, h at -1. Well, I'm just going to use this, and I'm really just going to say that, okay, well, h at -1 is equal to f at -1 over g at -1. Okay, going up to my table, f at -1, f, make sure I'm in the right row. So f at -1 is 3. So f at -1 is 3 over g at -1. G, this row right here, g at -1 is -2. Okay, so that looks like h at -1 is equal to -3/2. So I can kind of just drop that in. Y minus -3/2 is equal to, okay, and now I'm ready to find h prime at -1. All right, well, I'm back to this, and I'm looking for the derivative now of h, and so I'm going to have to use quotient rule. Okay, so let's just do this. H at x, let's give yourself a little room, man. H of x is equal to f of x over g of x. And so h prime of x, according to the quotient rule, is going to be a why not? I'm going to bust out my u's and my v's. So prime is going to be f prime of x, and v prime is going to be g prime of x. So quotient rule is going to be u prime, which is f prime of x, times u prime v, which is g of x, minus u v prime, all over 2a. No, that's not it. All over v squared. So it's going to be g at x squared. Okay. All right. Now I just have to drop in. I'm looking for h prime at -1. So I'm just going to change all these x's into -1. So just x equal to -1. Hope you don't mind. I'm just going to erase all my x's. All my x's live in Texas. So goes away. Replace all those with -1. -1, -1, -1, and -1. Okay, so let's make life easy. Let's take this, copy it, and bring it up to the table. We drop in values. Okay, so there's that. And so we need f prime at -1. So f prime at -1 is 1. I'm just going to write it above it. So I got 1. G at -1. G at -1 is -2. Minus f at -1, which is 3, times g prime at -1. G prime at -1 is 1. All over g at -1 squared, which is going to be -2 squared. -2 squared. Okay. Okay. It's probably going to be easiest just simplify just a little bit. Don't tell anybody I'm doing this. So I got 1 times -2, that's -2 minus 3 over 4. Well, it looks like it's -5 over 4. So -5/4 is my h prime at -1, -5/4. -5/4 times x minus -1. Okay, and there is my equation for my tangent line. Okay, all right. Let's go ahead and dive in. Question 2. Particle moving along the x-axis has velocity v at t, feet per second at time t seconds, or the closed interval from 0 to 10. The graph of v at t shown above consists of 4 line segments and a quarter circle. Okay, so it looks like this last part right here, purple, that's my quarter circle, and I've got my 4 line segments leading up to that. Okay, part A, find the average acceleration of the particle on the interval from 0 to 10. Include units in your answer. Okay, well, I know average acceleration is really going to be v at t minus v at 0 over 10 minus 0. So now I'm just pulling values off my graph. V at t at 0, v at 0 is 1. So 0 minus 1 over 10 minus 0. I'm going to leave that. That's a numeric answer. And that's going to be my units. Well, I can think the units for velocity are given as feet per second and time t seconds. So this is going to be feet per second times seconds. Or I could just call that feet per second squared. Okay, right like that. That's going to work too. Either way, I want to do this. -1 over 10 feet per second squared. Okay. Part B, at what time t is the particle furthest to the left? Right. That's a really good question. If we think about it, this is velocity. And when velocity is positive, so when vt is positive, the particle is moving to the right. Particle moves to the right. When v at t is negative, particle is moving to the left. Okay. So this point, let me just change this up. Got red, negative. That was okay the way it was, but I like blue. Okay. So I'm just going to say, well, velocity is positive over this interval. And I'm going to save time because I think they're going to ask me this later. I'm going to put time, and then I'm just going to put position. I'm going to say S at t, that's position. Okay. Well, they don't tell us in this problem what the position of the particle is at time 0. So at time 0, we really don't know what the starting position is. It could be, 0, it could be -2, it could be 5, or wherever. It's not really going to matter because they're not going to really have another question that's based on the initial position. So we can really make up whatever we want. Maybe to keep things simple, we can just say it's going to start at position 0. So at time 0, it's at 0 on the x-axis. Okay. All right. And then when we say go, the particle starts to move, first off, it starts moving which direction? Well, it starts moving to the right because velocity is positive. And so in this interval from 0 to 3, so from 0 to 3, our particle moves to the right. Well, how far to the right does it move? Well, the distance it moves to the right is going to be given by the area under the velocity function above the x-axis. So I'm counting squares. I'm just seeing, okay, there's a square. 1, 2, these two squares together make another square, and that's a 1/2. This square right here would be a half. So that area under that curve is 3.5. So at time 3, my particle, if it started at position 0, my particle is 3.5 units to the right. So it's at 3.5 on my x-axis. Okay. All right. Now at time 3, what happens? Well, the particle stops and then it starts moving to the left on the interval from 3 to 6. And I can see here, well, the distance it moves to the left is given by the area of that triangle there above my function below the x-axis. Well, it looks like the triangle has a base of 3 units and a height of 1 units. So that would be 1/2 times 3 times 1, or 3/2. Okay. So that would mean that the particle moves 1.5, 3/2, 1.5 units back to the left. Well, if it was at 3.5 and it moves back 1.5, well, now it's located at what position? Well, it'd be 3.5 minus 1.5, and that's going to be at 2. So the position of the particle is at 2 units to the right of the origin. Okay. All right. My next interval is going to be to time 7, kind of right before that quarter circle starts. And here we've got a triangle. Well, that's going to be 1 unit. That's going to be 3 units high. So again, the area of that triangle is going to be 1.5. I didn't write that. Area was 1.5, and then we reckoned it as negative 1.5 because it was where velocity was negative, it was moving 1.5 units back to the left. This one is going to move 1.5 units to the right. So what's the position of the particle? Back to 3.5. Okay. Now, the last interval from 7 to 10, particle is moving to the right. So it's going to be time 10. And we just have to figure out what's the area under that quarter circle. So we're really kind of looking for this area right here. Well, the way we're going to get that is we're going to take the area of this 3 by 3 square. So that would be 3 by 3. 3 times 3, 9 square units would be the area of that square. And I want to subtract the area of my quarter circle. So this area, I want to subtract from that. Well, the area of that is going to be given, I'm subtracting that. Well, that's going to be 1/4, it's a quarter circle, pi r squared. And my radius is going to be r. So that's going to be 3 squared. Okay. So 3 squared minus 1/4 pi times 3 squared is going to be the area of this blue region right here. Okay. Sweet. Okay. Well, that was a lot of fun. Now the question is, we kind of built this table and we're working on part B, and it says at what time t is the particle furthest to the left? Well, we got a table of our positions here. And so we're basically looking, this is really, you might not realize it, but this is kind of an absolute minimum question. We're looking for the absolute minimum of position, okay, which I just happen to call S and T in my table. Well, the minimum position, you got 0, 3.5, 2.0, 3.5, and then whatever 3 squared minus 1/4 pi 3 squared, okay? Whatever that is going to be all my positions at those 1, 2, 3, 4, 5 times. Well, what's the minimum position, or the position where it's farthest to the left? It'd be that. And now what I want to know is what's the time when the particle is furthest to the left? Okay, well, that's going to be at time 0. Okay, so I'm going to say at what time t is the particle furthest to the left? I say at time t equals 0. Okay, now this problem didn't say anything about like justify your answer or explain, but I would probably just do the table, and I would say, you know, see table for position. S of t. Okay, sweet. Okay, part C, we're going to like our table again, find the total distance traveled by the particle on the interval from. Okay, I'm going to copy our table down here. And if I'm looking for total distance, what I'm looking at is I can kind of take and say, okay, going from each position here, I'm going to do, how about this? This would be displacement, and then this is going to be total distance. So I'm going from 0 to 3.5. Well, that is 3.5, which is total distance. It's also 3.5. Now I go from 3.5 back to 2.0, which displacement would be negative 1.5 units. But for total distance, that's going to be absolute value of negative 1.5. Okay, I guess we can think of all of these as absolute value. The positive ones aren't going to be impacted, only the negative when it's moving back to the left. Okay, and then from 2.0 to 3.5. That displacement is 1.5, and total distance is 1.5. Okay. And then the last segment, going from 3.5 to 3 squared minus 1/4 pi times 3 squared. That displacement would be exactly that's going to be the way I want to do that is I want to do 3 squared minus 1/4 pi times 3 squared minus 3.5, and then total distance is just going to be the absolute value of that. Which, again, the only one the absolute value is going to affect is this one right here, where the particle moved back to the left. Every other interval, the particle is moving to the right, and so the displacement is equal to the total distance for that interval. So really, total distance-wise, I just want to pull this all together. So I'm just going to take this 3.5 plus absolute value of negative 1.5 plus 1.5 plus this hot mess right here. 3 squared minus 1/4 pi 3 squared minus 3.5. Okay, that's going to be the total distance traveled by the particle. Okay. Okay. Part D. Okay, last part, and I think you're going to like this one. On what intervals is the particle slowing down? Well, by slowing down, we also could say on what intervals is the particle's speed decreasing? And we do need to justify your answer. Okay, if we remember that speed is equal to the absolute value of velocity, here's what we can do. Here's our velocity function, right? Well, we can just say, okay, speed, I'm going to do in red here, and I'm just going to say, okay, well, gee, speed is velocity when velocity is positive, right? Okay, so those portions of the velocity where the velocity is positive are also going to be the speed graph. It's just this portion here where velocity is negative. So what I got to do basically is what? Just flip that. So I'm going to take this and just flip it over the x-axis. So that's going to go up here like this. Okay. Sweet. All right. So that in red, that is the speed graph. Okay, well now it's really easy to see, gosh, where is the particle slowing down or where is the speed decreasing? Well, the speed is decreasing. If I'm looking at the speed graph, it's not hard to do. On this interval, going down, going down, going down. So those intervals would be from 1 to 3, 4 to 6, 7 to 10. Okay, so I'm going to say speed is decreasing on the intervals 1 to 3, 4 to 6, and 7 to 10. Some union symbols there. Okay, now justify your answer. Okay, because what? The speed is decreasing when v of t and acceleration, which is the derivative of velocity, have different signs. Okay. Now, a tougher way of doing this problem without just flipping it, making it into the graph of speed and then looking where its speed is decreasing would be to just look only at velocity and just say, hey, you know what? I need to pick those points where when velocity is positive, that velocity is decreasing, okay? Or where velocity is negative, velocity is increasing, okay? If you look at it that way, you're going to get the exact same intervals we got when we're just looking at the graph of speed, okay? All right, guys, hope that helps. Thanks.